Okay, so we are going to work on this example over here. Okay, we're going to work on this example over here. So before the break, I show you how the boundary condition changes. Okay, so we're going to find the deflection equation. Okay, so find the deflection equation of the beam. Okay, so we find the deflection now. Okay, so if we look over here, so how many boundary conditions we have? So we have boundary condition number 1, boundary condition number 2, boundary condition number 3, and we have boundary condition number 4. It's good news if you have 4 boundary conditions. If you have 3 boundary conditions, start to panic. Okay, more than 4 is okay, less than 4 is not very good. So the first thing we're going to form is the equation, right? We're going to find the equation of the distributed load. Okay, we will find equation of distributed load. So we know that it's a gradient distributed load. If this is x, this is omega, over here is omega naught, right? It stops down here, and down here it stops at a certain distance L, right? So the equation is omega as a function of x is equal to delta y over delta x multiplied by x. Now the y-intercept is equal to 0. Okay, so this is the equation of the distributed load. So this is equation number 1. Okay, so once you form this equation, now what you realize that I did not do first step is to find the reaction at point A and point B, right? I did not need to do that. Okay, for this technique, there's one thing unique about this technique is you don't need to find the reaction at point A, point B. Some cases you need to, but for simply supported beam, you don't need to. Okay, so from here, we're going to substitute equation 1. Right, into dv by dx is equal to minus omega as a function of x. So this will be equal to dv over dx is equal to minus now omega naught over Lx. Okay, so this is our equation number 2. Then we're going to integrate. So we're going to integrate, right? So integrate number 1. So v as a function of x is equal to minus omega naught x squared over 2L plus by C1. Okay, this is our, okay. Now, why plus by C1? Because I'm integrating without any limits. Okay, so that's a constant. So this will in fact is equal to dm by dx. So that is our equation number 3. Now, can we find C1? If you look at our boundary condition over here, we don't know any boundary condition at all. Okay, move on. Okay, move on. Then m, then we integrate the second time. Right, so m as a function of x now is equal to minus omega naught x cubed over 6L plus by C1x plus by C2. Now this is equation number 4. Okay, So equation number 4, we have two boundary conditions, right? We can use two boundary conditions. One boundary condition is over here when m is x equal to 0, m equal to 0. When m is equal to L, x is equal to 0. So we're going to substitute, right? X is equal to 0, m is equal to 0 into equation 4, right? So what we get is 0 is equal to 0 plus by 0 plus by C2. So therefore, C2 is equal to 0. Okay. So usually when I do this, I usually like to draw a line to let me know that I've used the boundary condition. Then we use the next one. Okay, so we're going to substitute. We're going to substitute x is equal to L. Okay, m equal to 0 into equation number 4. Right. Now remember, now equation number 4, C2 now is also equal to what? 0. Okay, so that's you stand. So when you substitute that, you get 0 is equal to minus omega naught L cubed over 6L, right? Plus by C1L, right? So now you can get rid of this, get rid of this squared. So C1 is equal to omega naught L over 6. Okay, so that is your C1. So therefore, m as a function of x now is equal to minus omega naught x cubed over 6L, right? Plus by omega naught L over 6, right? You have to include x, and this is equal to your equation 4a because it's from equation 4. Okay, right? So we know we're going to apply. Okay, we're going to apply the elastic curve equation. Into equation 4a, right? So we know that EI d squared yi over dx squared plus is equal, so not plus, is equal to m as a function of x, and then is equal to minus omega naught x cubed over 6L plus by omega naught L over 6x. Okay, so this is equation number 5. Then you integrate again. So this is integrate number 3. I told you, right? It's easy, right? It's all simple integration. It's only you have to know your boundary condition. Okay, so EI dy by dx is equal to EI theta, and this is equal to minus omega naught x4 over 24L plus by omega naught L x squared over 12 plus by C3 now. So this is your equation number 6, right? So any boundary condition you know regarding theta, the answer is none. Okay, so we don't know any boundary condition, but we do know boundary condition when for the deflection. So slope, we don't know any boundary condition, so we know. So we're going to integrate again. Okay, we're going to integrate the 4th time. You have EI dy by so EI y as a function of x now. So slope is also as a function of x. So this is equal to minus omega naught x5 over 120L plus by omega naught L x cubed over 36, right? Then plus by C3x plus by C4, right? Then we're going to apply our boundary condition. We're going to substitute when x is equal to 0, y is equal to 0 also, right, into equation 7. So where we are looking at now is we are looking at this boundary condition over here, right? And because this is x is equal to 0, y is equal to 0, once you substitute in there, so you have 0 is equal to 0 plus 0 plus 0 plus by C4. So we know that C4 is equal to 0. Okay. So the next one is we're going to substitute x is equal to L, deflection y is also equal to 0 into equation 7. Now knowing that C4, right, is also equal to 0. Right. So when that's the case, I'm going to split this page into two. Or not, if I flip over pages, I'll get headaches. So for this case, you will get 0 is equal to minus omega naught L4 over 120, right? Plus by omega naught L4 over 36 plus by C3L. Okay, so minus 1 over 120 plus by 1 over 36 is equal to 7 over 360 positive. 0 is equal to 7 over 360. Omega naught L4 plus by C3L. Right. So we can find that C3 is equal to 7 over minus 7 over 360 omega naught L cube. Okay. So from here, EI y as a function of x is equal to minus omega naught x5 power 5 over 120L plus by omega naught L x cubed over 36. Okay, and then minus 7 over 360 omega naught L cubed power multiplied by x. Okay, so this is the equation of your distributed of your the equation of your deflection, right? Right, and then so at any position x, okay, and this is valid when x 0 x to L, okay, and as long as your x is between that limits, this equation will work. So you can find at any point how much deflection you're going to get. Okay, so likewise, if you want to, you can also find the slope. All right, so the slope equation is minus omega naught x4 over 24L plus by omega naught L x squared over 12, then minus 7 over 360, right, omega naught L cubed. Okay, so that the equation that I've just written again is only valid in this limit. And let me see what equation. So this is equation number, so this is equation 7a, and this is equation 6a. Okay, so is that straightforward, right? It's not that difficult at all, right? Now I'm going to the strength of this technique is it can find statically indeterminate structure. Okay, I repeat again. The strength of this is able to find statically indeterminate structure. So I'm going to do another example. Okay. Now, so if we look at over here, this structure over here is statically indeterminate, right? Okay, it's statically indeterminate, and we're going to do this example now, right? Using the only way to solve this is using the elastic curve technique, or the integration method together with the elastic curve technique. Okay, so let me elaborate. So let me